Welcome back, everybody. I am here with Simona from ADOC, here to tell us about auditing data and here to help me with my pain and trauma of managing Kafka, Kafka brokers and clusters and all the rest. Simona, if you would, please help me understand what I did wrong.
Okay, so we are going to talk quite a bit about Kafka today. And I officially welcome you to my session, Auditing Data and Answering the Lifelong Question, is it the end of the day yet? Now, if you're not familiar with that question, don't worry about it. We're gonna talk about it in quite length in the next 45 minutes. So what are we going to talk about? We're gonna start off with Nielsen's architecture, and we'll really see how it had little fires going on everywhere, and really understand the need for an auditing system. We'll then talk about designing our metadata. What does our auditing data even look like? How to store it, and all the optimization work we did to actually query it for optimum. We'll then go back to that end of the day question, and maybe we'll finally get an answer. And then some alerts and add-ons to just top it all up. But first and foremost, the most important thing, who am I? So who am I? I'm Simona. I'm a big data engineer at ADOC, but I did work at Nielsen for up to a few months ago. So this is totally based on a true story. I love data. I've been dealing with data for the past 10 years now, which feels like a lot. 29 years old, joining you here from Israel. I love music, the weirder, the better. And I love traveling. So this is basically me in a picture. So the most important thing to keep in mind while looking at Nielsen's architecture is that more than 50 terabytes of data, billions of events flow into this architecture daily. We collect them from various devices, cell phones, TVs, computers. They get collected into our front-end layer. Our data serving servers in this cubicle right here are written in Java, and their SLAs are very, very important to them. So the data gets collected there, and it's being produced into this Kafka cluster. Now, it's important to notice that the front-end layer is regional. So at the time, we had several clusters all across the world, each running its own front-end layer. And so each one of these was running its own Kafka cluster. I'm sorry for all the post-trauma. From there, the data is replicated using the uReplicator into that one central Kafka in AWS, a really big cluster of about 50 brokers. From there, we have the data loaders, which are essentially just Spark streaming applications. They consume all that data, they deserialize it, and they just spill it into RDR. RDR stands for Raw Data Repository, and it's just our data lake sitting there in S3. From there, we have our scheduled Spark jobs, the data processors. They're responsible to, again, consume that data, enrich it, aggregate it, and eventually store it in each one of these different data stores. So we have Druid, Postgres, and also back into RDR, back into the data lake. Our application layer consists of several different applications, so reports, billing, data science, and they are the consumers. They consume that data either through these different data stores or altogether through Hive. What could go wrong? So let's talk about what could go wrong, because this architecture really had little fires going on everywhere. And what we'll do now is actually just go into a bit of a discussion discussing these arrival pain points. So first, I want to just zoom into this connection between the regional data centers and their Kafkas and that one central Kafka on AWS. So we were doing the replication using uReplicator. And if you're not familiar with the uReplicator, it's a project by Uber. It's based off of Kafka's own mirror maker. And so it suffers from essentially the same problems as the first mirror maker suffered from. What do I mean by that? Well, aside from the uReplicator just crashing and stops working, so no data is flowing into that one central Kafka on AWS, something worse could happen. What do I mean by that? Well, let's say that you have a pretty big topic. Let's say it's 1,500 or 2,000 partitions big. So sometimes the uReplicator would stop working, but not on the entire topic altogether. It would just get stuck on some 10 or 20 or 50 partitions. So essentially, most of your data is still being replicated. Most of your data is still flowing, but some of it, just some of it is not. And we're a data company. So data integrity is very, very important to us. So this was becoming a pretty big problem. Now let's talk about what happens after data is arriving into that one central Kafka in AWS. What could go wrong here? Well, some brokers crashing or entire Kafka clusters crashing. So Kafka is essentially unavailable. Data gets delayed, arriving into RDR. Or even the data loaders crashing, and you have alerts popping up when people are looking at the alerts. But essentially, data is being delayed. Data is not arriving into RDR. And what didn't I discuss while talking about all of these arrival pain points? I didn't discuss how we actually recovered from them. So if we look again at this connection between the regional data centers and our Kafka and AWS, how did we recover from this failure? Well, we just restarted the uReplicator, right? So uReplicator is working again, data is flowing again. Again, it's arriving into Kafka and AWS. But how much do we actually know about the arrival rate of our data? What did we know after the uReplicator got started again? Did we have some data loss? Did we have some data duplication? We had no visibility. We had no knowledge about these things. And again, if we look about what happens after data arrives into Kafka and AWS, so alerts started popping up, we restarted the Kafka cluster, we restarted our data loaders, data is again flowing into RDR. How much did we actually know about what was happening to our data after each and single crash? So the answer is we didn't know. And that was a big, big problem. And at this point, I actually want to start discussing the end of the day question and what it actually means. So its importance comes from the media world, because in the media world, the way that we actually want to process our data is on a daily granularity. We want to perform daily unique counts of our users. So when we talk about the data processors and we talk about them being Spark jobs scheduled to run on that raw data, they need to run on a daily granularity. They need to run on all of yesterday's data. So when we talk about the end of the day question, the question is actually, did all my data actually arrive? Can I run my data processor now? Is yesterday over yet? Because if the data processor ran, but it didn't run on an entire state of data, then we'll have to rerun it again. We'll have to reprocess all that data, and that would cost us quite a lot of money. So at first we said, let's try to solve this problem. Pretty straightforward. We were using Airflow as our scheduler, and we said, okay, so when is the day over? Is 11 a.m. good enough? Like, if I run my processor at 11 a.m., then yesterday's probably over, right? But that one time we had a Kafka outage, no data was flowing in for some time, then our data processor run, and we had to actually rerun it again. So we said, okay, you know what? Fixed time, not a good enough solution. We need a different indicator. What can we use instead? So we said, okay, let's just use AWS S3LS. That way we can know when was the last file written into the bucket, and we can use that as an indicator. So let's say 2 hours have passed since data has arrived. Then we can run our processors now, right? But then again, we had an outage and data didn't arrive for quite time. And again, our data processors took it as an indicator that the day was actually over. But it wasn't over. Yesterday was not over yet. And so we came to the conclusion that these two answers weren't just good enough for our problem. And this is a pretty big problem, because again, let's look at it in the context of this architecture. We have an outage with Kafka, we have a problem with the data loaders, data is getting delayed, arriving into RDR, The data processors are not aware. They start running. They run on partial chunks of data. They store all of these partial conclusions into each one of these different data stores. And the problem doesn't stop there, because if we look at the application layer, BI, reports, data science, some of them are actually producing their own data sets. So it's not only the data processors that have to run again, it's all of these applications also have to get acknowledgement that it's the end of the day and that they actually can run their calculations. And so if we look at this architecture now, again, I think you'll really see that it had little fires going on everywhere. And so for both of these reasons, for the data arrival pain points and our problems with data integrity, and to finally get an answer to this question, is it the end of the day yet? We've decided to design our auditing subsystem. And so at this point, I wanna start discussing this data. I wanna start discussing this design solution. And first, I want you to keep some points in mind. So the first point that you need to keep in mind is that we didn't have one Kafka topic. We had several Kafka topics. And that number was not fixed either. So if tomorrow there's a new type of data, a new type of need, we are going to define a new Kafka topic. The second several points have to do with our data serving infrastructure, and I've actually mentioned some of them before. So that infrastructure is written in Java, and there are 2 JVMs running on every single machine. And so each one of these JVMs is working against a couple of topics. So they're getting the data, doesn't matter, it's just like generic type of data, then eventually they produce it to the relevant topic. As I've said, SLAs are very, very important to them. And finally, we were not just using a Kafka producer, we were using our own Nielsen Kafka producer that had several additional layers. And so because we wanted to know the exact number of data actually produced to Kafka, we decided to implement the auditing system on our Nielsen Kafka producer. And because of the SLAs, because of how important the SLAs are, we really needed to write our code in the most optimized way possible. The last point that's really important to keep in mind is the fact that we use AVRO. So we use AVRO in all of our topics, and you'll see how this will actually make our job a lot easier. So finally, yeah, what's a window? Why is the word window written on my screen right now? What's an auditing window? So the auditing window is our metadata object. And we use the word window to refer to a time frame, right? Because we're not going to just audit everything forever. You need some sort of a time frame. And we decided on a time frame or a window of 5 minutes. If you ask yourself why 5 minutes? Well, it's because we said, okay, 1 minute, that's really small. And then 1 hour, that's quite a lot. But 5 minutes, that sounds good. And we wrote our code in such a way that this time frame, this window is configurable, but we never actually changed it. So it stayed on 5 minutes. So what are we going to collect? How is this metadata object going to look like? Well, we're going to collect for every process running on every server, producing against every topic for every 5 minutes, right? So that the audit time, the amount of messages that were produced. And what you see on the screen before you is just that AVRO definition of this object. Cool. So now that we actually have our metadata object, we need to connect it to the data. And the way that we're going to do that is we're going to create an auditing header that will have all that complementary information that our data does not have, so that we'll be able to perform the comparison of the amount of messages we counted against the amount of messages that actually arrived to the other side. So our audit header is going to consist of that key, of that same window timestamp, server name, and sequence ID. And sequence ID is a bit of a spoiler. we're going to talk about it later on. So just look at window timestamp and server name. Cool. So if we look at the context of the original AVRO model, so you get to see here an anonymized version of a raw event data, right? So we have several fields. We have the header field, we have some field and some field too. And what we're going to do is we're going to add to our AVRO model the audit header, and then we're going to inject it into our data. How are we going to do that? Well, the code looks exactly like this. Since I've told you before that one data serving server is actually dealing against, it's producing to several topics. So we're getting this generic AVRO record. So what we're going to do is we're just going to get that schema of the generic record, and we're going to first check if the header is even there. And after we do that, we just get the position of this field in the schema, and we just run it over with our information, with our audit header information. Cool. So if we look at it again in the context of this architecture, everything we've just discussed is happening right here. It's happening in the data serving cubicle. So information is flowing in, we're injecting it with the audit header, and in the meanwhile, we keep creating every 5 minutes, every window, a new metadata object, and we're eventually producing both of them to Kafka. And you might have noticed that there's a bit of a problem here, because producing both of them to Kafka actually means that we're trying to audit Kafka with Kafka. And yeah, we noticed that as well. Actually, after we implemented the solution, we said, hey, that sounds a bit wrong. So we said, okay, not a problem. What else can we do? And we've used a service by Amazon called Amazon API Gateway. We've implemented a simple Lambda in Scala that would accept this auditing information, parse it, and then ship it off, store it in our auditing table that we're going to discuss shortly. But instead of just replacing the Kafka topic solution, we said, no, we're going to keep both. Why is that? Well, first of all, the Kafka topic solution was already working. It was already there. And the second reason is because we discovered that when we use both of these solutions, we're really covered. So if there's a problem with Kafka, we have the gateway. If there's a problem, a momentary problem with the gateway, we're still not going to use any windows because we have Kafka. So that's why we've decided to use both. Cool. So if we again look at it in context, data serving, collecting the information, producing our data into Kafka, and then they're producing our auditing windows, the metadata objects to Kafka, but they're also shipping them into the Amazon gateway and the Lambda function responsible for receiving that information. Cool. So now that our data is actually arriving into the data layer, we have to consume it. And we have two types of data, right? We have the auditing window, that's auditing metadata, and we have the audit header that is part of our data now. So we've sort of already discussed how to consume the audit window. So if it goes straight through the API, there is no consumption work there. The Lambda is parsing it, storing it in the table. And then for a Kafka topic, we just created a simple Kafka consumer that would work against that audit window topic, consume that data, store it in the table. So what happens with the audit header? Well, together with the rest of our data, it's just being spilled into RDR. So we've created a set of consumers consuming from S3 only the audit header. So these consumers are pretty lightweight. They consume the audit header, aggregate it, and then store it in the same table that we'll see in just a moment. And we actually ran all of these consumers on the same EMR. So if you're not familiar with EMR, it's a service by Amazon, Elastic MapReduce. Essentially, it's a cluster with some predefined software, and you can run your consumers on it. And more than that, you can run a couple of steps, a couple of applications in parallel. So we just ran all of our consumers on the same cluster. And again, in the context of the architecture, this is just everything we've just discussed. So the same data loaders are spilling the audit header into RDR. From there, we have the audit header consumer. And then for the audit window, we have the audit window consumer and the Lambda function. And then eventually all of that data ends up in the same table. So let's talk about that table now. So I think if we revisit our audit data, and if you think about it again, that the data is structured. And we have a very evident key and a value. So we've decided to store our data in a PostgreSQL table using the Amazon RDS service. So we started by designing our table. We said, okay, there's a set of questions that we need answered to address all the pain points, all the arrival pain points that we've discussed before. So what are these questions that we want answered? First of all, we talked about the level of granularity that we need. So we'd like to know answers on topic level, on server level, on process level, right? But what about some additional levels of granularity? We talked about the front end layer running on different regions, right? Running in different clusters across the world. So what about regional level? That would be really cool, right? And then the two additional questions. So the first one, arrival rate, that's pretty straightforward, right? So that would be how much of the data that was actually produced arrived at the RDR. And then arrival latency is a bit less straightforward, and that's just how much of the data that was produced actually arrived within 1 hour or 2 hours or 3 hours. So now that we have all of these questions predefined, let's design our table. So of course, we have our evident key that you should all know by heart right now. That would be the audit timestamp, the topic, the server, the process. Then we have the event count, which is essentially our value, right? So that's just the number of events that were actually counted for this key. What is location? What is the location column doing there? Well, we've decided to store all of our data in the same table and just differentiate between the metadata and the audit header using the location column. And then you can also see the add-ons that we've just discussed. So we're going to use region. We're going to have a region column. And we're going to have an insert time column just to calculate arrival latency, right? So insert time is just the time that the data arrived into the audit table. And then if you just deduct the window timestamp from the insert time, you get the amount of time from the moment that the data was produced to the regional Kafka and up until the moment that this metadata arrived at the audit table. And if we look at an anonymized version of this table, you can see the topic name, right? So today we're playing with topic 1, topic 2, and topic 3. You can see the server name. The way that we actually enriched our data with region, we just extracted it from the server name. I wouldn't say that it's the best possible solution, but it was the quickest one. Process ID, it'll be really important to mention that window timestamp and insert time, they're all in UTC, right? We're working cross region. Some of our developers are in Israel, some of them are in the United States. So all of our timestamps here are in UTC. The location, you can see Kafka windows and RDR headers, right? So just to differentiate and understand what's the type of data that we're dealing with. And then I want to draw your attention to something interesting. So if you look at the event count column, you can see pretty big numbers there, but then you can also see a 0. What's a 0 doing there? That's pretty peculiar. But if you'll take another look, you'll notice that these zeros are only for location Kafka windows. So as I've said before, there's a process that's part of our Nielsen Kafka producer that's running in the background, creating these auditing metadata objects. And so even if no data is flowing through that server, even if the server itself is not producing any data, these objects will still get created. And so there will be created objects with an event count of 0. And that could be totally normal, right? Maybe the server is not getting any traffic. Maybe it's just a test server. But this could also indicate a problem. So this will prove very, very useful in just investigating issues. Cool. So what you see before you now is just the logo for Apache Superset, and that's a BI tool that we use at Nielsen Israel. And what we're going to do now is just look at some pretty Superset charts with our auditing data. So the first chart that I have for you is that data arrival within 3 hours. And data arrival within 3 hours is that latency question that we've discussed. And I think that you'll notice that the number is slightly higher than 100. So yeah, so we did have some duplications and some data loss problems in our system that we were just totally unaware of. But yeah, just a bit over 100, that's fine, right? Essentially, in the big data world, we're dealing with such huge volumes of data. Some data duplications, some data loss, it's acceptable. But when you see this number going over 150 or over 200, you know that you have a problem. Some more straightforward charts. So we have just the total data arrival within 1 hour, within 24 hours. And then eventually I also have the SQL query for you that was used for most of these charts. So you can see that we are actually calculating the latency using the deduction of window timestamp from insert time. And we're conducting the different counts just by using the location column with the case when. So yeah, that's pretty cool. So what you see before you now is, again, Superset's logo, but it's also the logo that Superset use when they keep loading data and your query keeps running and you're waiting. And we saw that logo quite a lot. And so at this point, I just want to do a little shout out to my dad, who was a DBA programmer for some 30 years more than me. And when I came to my dad with a problem, I told him our queries are running for 1.5 minutes. He didn't give up and he made it run for 15 seconds. So thanks, Dad. So how did we do it? How did me and my dad actually optimize our queries to run in an acceptable time frame? So the first thing we did is actually pretty straightforward. We just weekly partitioned the data. Most of the time we're running on dates. The weekly partitioning makes a lot of sense. Then the second thing we did is also pretty obvious. We created the unique indexes on the tables. We've created complementary indexes. We looked at the queries that we're running, most used predicates, and then using that as an indicator, we've created the complementary indexes. Now, my third point talks about Postgres and processing in parallel. So if you're using Postgres on RDS, I really, really encourage you to look at the 3 variables written on my screen right now. So that's the max worker processes, max parallel workers, and max parallel workers per gather. They are not configured by default on RDS, and you will be surprised with what 10 workers instead of 2 can do to your query. Another thing that we did is actually just create an entire process that offloads data to history. I think if we talk about log data and metrics and auditing data, most of the users don't really look at old data. It's not like we're gonna do, I wonder what happened 2 months ago or a month and a half ago. So just defining that reasonable time frame and then taking all of that old data and then just analyze it, store it in a different table. It's not needed on the main table. And then last but not least, tricking the optimizer. So I know that most of us think that the optimizer is the best and it knows best. You just submitted a query and it'll do its magic. But you will be surprised if you have an in predicate with like 2 or 3 values, and just instead of using the in predicate, you use a union instead, with like 2 or 3 queries union in between, you'll be surprised what that will do to your query. The things that you have to trick the optimizer to discover. Cool. So now that we have our data, we've collected it, we understand what it looks like, and our queries are actually running on it and getting us answers in reasonable time, let's go back to the end of the day question. Let's see if we can actually answer it now. And we came to the conclusion that we did, and we'll discuss that in a moment. So we decided to create a simple, again, REST API service that our data teams will be able to query, right, by topic, by region, by time spec. And that API will just give them an answer. Is it the end of the day yet or not? So how can we answer that question using the data that we have? So I have here for you the pseudocode for that method, but no, I'm just kidding. I've summed up all the questions for you, and we have 3 main questions that we need answered in order to say that yesterday is over. So the first question that we need answered is the data arrival rate for the entire scope over that threshold? Because I think that's the most trivial indicator. If it's under the threshold that you need, or if it's above, then the data arrival rate is not right, and the day is probably not over yet. But it's not good enough, because let's say our auditing system is not working at all, like something went completely wrong. So that's why the second question is here. So let's say, okay, our data arrival rate is fine, everything's fine. Now let's count the amount of audit windows that actually arrive in the system for that entire scope. Okay, so our data arrival rate is fine, the number of auditing windows is fine. Why is the third question written here? Arrival rate for the last window. Well, if I take you back in memory lane to all the superset charts that we saw, you'll remember that we had numbers higher than 100. So let's imagine that we had this day and there was this peak of data duplications, a crazy peak. And the day is not over yet, but you're trying to query it. What will happen is that data duplication peak will create a skew for the entire calculation, and you might falsely think that the day is over, but it's not. So we decided to use the last window, the arrival rate of the last window, as an extra indicator. So if the arrival rate is in the right number, and the amount of audit windows that arrive for the entire scope is acceptable, and also the arrival rate for the last window is just okay, then yes, yesterday's over, and the data processors can run now. Cool. So we're at the very end, and I hope you're holding up, and also that I'm on time. So some alerts and add-ons. So using the data that we've collected, we did create some alerts on the different granularity levels that we've discussed. And that really helped us a lot, because if you get an alert on the region, then the problem is probably with the your replicator and not with the data loaders and not with your main Kafka cluster. If you get an alert on the topic, then probably the problem is not with the your replicators, it's with the data loaders. And these alerts were popping up quicker than the your replicator alerts and the Spark alerts when the jobs crashed. And that was pretty amazing. And before we continue, I have these alerts for you here. So yeah, we're just querying the table and then shipping an alert straight to Slack. Cool. So detecting duplications. When I talked about the audit header, you saw a sequence ID there. And I said, well, that's a bit of a spoiler. So yeah, we added a sequence ID for every message in a single window, in a single frame, that will identify that message inside of that audit window. Why did we do that? Well, because when we just started getting arrival rates that are higher than 100, we didn't say, yes, we have data duplications. No, we said, oh my God, what if something's wrong with this entire system that we've just created? how can we make sure that there are actual duplications in our data? So that's why we have added the sequence ID, and then just querying the audit header for a specific window timestamp will essentially give you an indication if you actually have duplications or if the problem is with the auditing count. The answer is that we did have duplications. And then last but not least, more locations. So we use the location column not only to differentiate between what's the metadata and what's the actual data. We also kept in mind the fact that our architecture is pretty big and we have a lot of points in that waterfall. And so as a future point, we really strive to just add more consumers and more points. And so just add more locations and collect more information about the way that our data does through the system. Yes, and at this point, I will ask you if you have any questions, because I'm pretty much done.
Simona, thank you so much. I'll give it a second for the chat to catch up, see if they have any questions. I had one though.
Yes.
You know, Kafka's got a whole bunch of built-in metrics to itself, like incoming bytes, and is there a reason you kind of made your own custom events instead of just trying to rely on those?
Yes, we've checked all of the metrics, and when we've designed this system, this was 2019, 2020, there was no actual metric that will tell you this is the amount of messages that were produced, this is that, like, none at all. And that's exactly why we've created this ourselves.
Makes sense, because it just, otherwise it kind of made sense to me, because otherwise you can know bytes and requests and stuff. That doesn't tell you a message has arrived, right? Like, and you were trying to figure out from your producers what the messages coming in were. Okay. And I guess one other question is, how long, roughly when you build all this architecture, how long was this? Was it like a couple weeks effort? It sounded like you kind of learned as you went along. Like, was it kind of an evolving thing for y'all to build this out?
So just most of the development process was on the Kafka producer side, just like creating that code that had to be in Java, right? That would create all this metadata objects. So that took roughly around 3 weeks. And the reason that it took that much time was essentially because, again, SLAs are very, very important. So we had to do a lot of integration tests and just make sure that their code is still running under the right SLA. And I think most of the time that was invested into this project is just the design and the thought behind what's the data that we even want to collect. How are we going to answer our questions?
Makes sense. But yeah, it doesn't sound like it added a bunch of overhead, and you obviously wanted to prevent that from overwhelming your producers. So, I don't see any questions. So Simona, thank you so much, and everybody else, enjoy your lunch break. We will see you all here resuming roughly an hour. I think about 20 minutes. I look forward to seeing you all then.
Thank you. Sorry for the post trauma.
I still love Kafka.